People will be amazed at how much information is available on such a secretive topic, making nuclear bomb. Like what kind of materials you should use, how to make those materials, and even nuclear bomb design. But still, after knowing all of this, out of 195 countries, only 9 countries have nuclear bombs. But why? What's make it so hard to make a nuclear bomb? And the even more important question is, why such secretive information should even be available? Now, to really understand what's going on, we need to look at the technical difficulties, some laws and regulation, and also some politics. First, let's look at the technical part. One of the biggest challenges in making a nuclear bomb is acquiring nuclear fuel. The two most common nuclear fuels are uranium and plutonium. But for a moment, let's just remove plutonium, because plutonium is not a natural element, and the fact that plutonium is also made from uranium. Now, the only option we have is uranium. But surprisingly, uranium is actually not that rare. It's more common than tin, the stuff that's used in cans, and 40 times more common than silver. But the normal uranium, which is uranium-238, is not suitable for nuclear reaction. What we want is uranium-235. The difference between uranium-238 and 235 is the uranium-238 is more stable, while the uranium-235 is very unstable and radioactive, which makes it perfect for nuclear reaction. But separating uranium-235 from 238 is very hard, because only the 0.72% of this uranium is uranium-235, and the rest of 99.28% is uranium-238. Now, to increase the concentration of uranium, we need to go through a process called enrichment. And this is the most difficult step, because the government uses many global monitoring methods to detect nuclear plants, which we will come back to that later. The most common and effective method to enrich uranium is gas centrifuges. To enrich uranium, it's first turned into a gas. The gas centrifuges use high rotational speed to separate uranium-235 from uranium-238 by exploiting the slight mass difference, because uranium-235 is slightly lighter than the uranium-238. Now, in theory, the enrichment process seems simple, but in reality, it's very complicated, because first of all, you need to get your hands on centrifuges. But the problem is, you can just import these centrifuges. Who's going to give you their own centrifuges? Which makes it very obvious that you are trying to make nuclear fuel. And the other option you have is to make it yourself. But to build centrifuges, you need special strong material like margining steel and carbon fiber. But the problem is, these two materials are usually used for military purposes, like making missile casing, centrifuges, and high performance engine due to their superior strength. And that's why there is a special organization called NSG, Nuclear Supply Group, which prevents the import-export of any kinds of material that can be used for making a nuclear bomb. And that makes it very hard to get these materials without authorization. And that's not the only way you can be found out. Working on these projects require a lot of money, estimately billions of dollars, which makes it hard for any individual or undeveloped countries to pursue these projects. And everything has to be hidden because of global monitoring, which we will come back to that later. These centrifuges consume large amount of electricity, and normally these nuclear plants have thousands of centrifuges. Like the Iran nuclear power plant has 19,000 centrifuges. Now, assuming a nuclear facility has only 10,000 centrifuges, it means it will consume around 20,000 kilowatt-hour of current every single day. And this sudden increase in energy consumption can easily raise suspicions that something is going on. And there is also one weird thing about these nuclear plants. Although there are 9 countries that have nuclear weapons, but there are 32 countries that have nuclear power plant. And that leads us to our next point, non-proliferation treaty. In the Cold War between US and Soviet Union, when both countries were trying to increase their nuclear warhead, and more countries were creating nuclear bomb with the help of other countries, like the UK made its first nuclear bomb with the help of US, and France made its first nuclear bomb with the help of both US and UK, and so on. As more countries were getting their hands of nuclear weapons, the possibility of starting a massive destructive war was also increasing. But on July 1st, 1968, a treaty was signed by 191 countries to stop the proliferation of nuclear weapons. And the IEA, International Atomic Energy Agency, played an important part in making this treaty and suggested that we should use nuclear power not to create bombs but to create clean electricity. And that's the reason why 32 countries have nuclear power plants. But this also raises another question. If 32 countries have nuclear power plants, so why they never try to make a nuclear bomb? And the reason can be explained by the quality of uranium, because there is a huge difference between the uranium that is used for nuclear weapons and the nuclear reactor. The nuclear reactor requires the uranium to be enriched by 3 to 5%, and on the other hand, the nuclear bombs require the uranium to be enriched by 90%, which is a huge difference. And to ensure the non-nuclear states use their nuclear plants for peaceful purposes, the IEA conducts inspection to make sure that they are not trying to make a nuclear bomb. The one way to find out if a state is using the enrichment facility for nuclear weapons is not just to see how many centrifuges they are using, but also how those centrifuges are arranged. Let me explain. Just for example, suppose if an enrichment facility uses 1000 centrifuges to make uranium enriched by 3 to 5%. What they can do is again enter the 3 to 5% rich uranium into the first centrifuge and repeat this process several times to reach 90% concentration. Now we want to talk about one important thing, and that is global monitoring. Even if someone try to build a nuclear plant, he can still be found out, and there are a lot of these methods. Let's quickly go through all of them. Satellite surveillance. Satellite can take pictures of nuclear facilities with high quality camera, and if a nuclear facility is hidden, then we can use infrared cameras to track nuclear plants, because nuclear plants generate a lot of heat. Seismic monitoring. The CTVTO Comprehensive Nuclear Test Ban Treaty Organization uses over 300 seismic monitors worldwide to detect underground nuclear tests by identifying unique seismic waves that differ from natural earthquake. Radiation detection. Ground-based sensor at borders, ports, and on aircraft can detect radiation from nuclear materials. Environmental sampling. Collecting air sample with high level of isotopes like iodine-131 and xenon-133 can indicate recent nuclear fission. Acoustic monitoring. Underwater hydrophone can detect acoustic signal from underwater nuclear test. These sensors are placed in the ocean to monitor underwater nuclear explosion. And last but not the least, the good old spice. Now, if somehow you manage to enrich uranium by 90%, although you wouldn't be able to without solving all of these problems, but let's just suppose that you did enrich uranium. And this is where the next point comes in. Bomb design. First of all, I wouldn't be going into too much detail because it's stupidly complex. There are mainly two types of nuclear bomb. The first type of nuclear bomb is fission bomb. Fission bomb works on nuclear fission. Whenever a nuclei absorb a neutron, which makes it unstable and split into smaller nuclei, and in process release a ton of energy, enough energy to destroy cities. The same type of nuclear bomb that was dropped in Japan on Hiroshima and Nagasaki, the little boy and the fat man. In order to detonate any kind of nuclear bomb, we need to reach critical mass. Critical mass is the minimum amount of mass that we need to sustain a chain reaction, and not just the mass but also the density, which I will talk about in a minute. The little boy uses two pieces of uranium, the one in the front and one in the back, and when the back part of uranium shooted into the first part, it reaches critical mass and the bomb explodes. But the fat man bomb uses a different method. Although both of them are fission bombs, in this bomb we have a core that is made of plutonium-239, but this time the bomb doesn't explode because it hasn't reached its critical mass yet. Now, in order for plutonium to reach its critical mass, we have to place explosive all around the plutonium in a way that when the explosive get detonated, it will create a circular shockwave that's going to compress the plutonium, and the shockwave has to be circular or otherwise the bomb not going to explode. We are doing all of this to increase its density because in the current plutonium, the atoms are very far from each other. If we try to explode the bomb now, it's not going to sustain a chain reaction, and that's the reason we must compress the plutonium to make its particle come closer. When the plutonium get compressed and reacts with the neutron generator inside the core, the bomb explodes. Now let's move to the interesting part, fusion bomb. Now this one was a bit surprising for me because my whole life I heard that fusion reaction is not even possible. It only happens on star and sun when two smaller nuclei combine to form a heavy nuclei and in process release a ton of energy. But the only problem is fusion requires heat, a lot of heat, around 100 degrees Celsius. Sorry, did I forget the million part? 100 million degrees Celsius, which makes it impossible to achieve. That is 6 times hotter than the core of sun. But then these two guys came up with the idea of creating a fusion bomb, aka hydrogen bomb. This bomb consists of two main parts. The first part is very similar to the fat man bomb, and the second part, this is where the fusion happens. First, the fission part gets detonated and generates a lot of heat, and then that heat is used to start fusion. And when it happens, a literal star is formed that is 6 times hotter than the core of sun on the Earth's surface, which destroys everything in its way. Now, to put it in a perspective how destructive these bombs are, let's look at an example. If we drop the little boy bomb with 50 kilotons of TNT on Tokyo, the bomb that was used on Hiroshima, it will impact 370 meters and it will kill around 120,000 people. And for the fat man bomb with 21 kilotons of TNT, which is 1.4 times more powerful than the little boy, it will impact 600 diameter and it will kill around 131,000 people. Now, this is where things get interesting, or should I say destructive. The Tsar bomba, which is also known as hydrogen bomb. This bomb has the power of 50,000 kilotons of TNT, which is 3,333 times more powerful than the little boy. If dropped on Tokyo, it will kill around 11.3 million people, and this much part of the Japan would be destroyed. Now, the interesting thing is this bomb was not supposed to be 50,000 kilotons of TNT, but 1 lakh kilotons of TNT. But in the end, they decided to reduce the power of the Tsar bomba so they can keep the damage under control. Now, the point of telling you all of this is to tell you how complex and destructive these bombs are. And in order to make these bombs, you have to be very precise and accurate. And the one thing I haven't even mentioned, that you are going to need some people with great knowledge about nuclear bombs. But the problem is, where are you going to find these people? there are only a few people on this earth that actually know how to make a nuclear bomb. Now to our most important question, why such secretive information should even be available? It just doesn't make any sense. Well, to understand this, we need to go back in time. During the World War II, the US created its first nuclear bomb in the Manhattan Project and bombed the two cities of Japan, Hiroshima and Nagasaki, and killed around 220,000 people. Now the US government, in order to justify the use of nuclear weapon and promote their role in ending the war, released a significant amount of information to justify their action. And after the end of Manhattan Project, the scientists and researchers returned to their institution where they published paper on nuclear physics and reactor technology. Now you might be thinking, what's the point of telling people how the nuclear bomb works, right? Well, the US government actually benefited from all of this. First of all, it's created trust between the people and the government. And the more people know about the destructive power of nuclear bomb, especially the people of other countries, it can stop them from going into war and help them sign treaties like the Non-Proliferation Treaty and the Nuclear Test Ban Treaty. And the knowledge about nuclear fission has also helped us in medical science. Without the understanding of radiation, things like cancer treatment, X-rays and CT scans wouldn't even be possible. So telling people about the nuclear bomb is actually a good thing. It creates trust and transparency and stop countries from going into war. Now we all know how destructive nuclear bombs are, but there are 5 more destructive tech that I think you should know about, and some of them are even more destructive than the nuclear bomb. Click here to watch that video and I will see you there.